Okay, for this next portion, you want to be over on the portal. So I've created a session here, and I'm in my home directory. I'll go into cd work classes cd ME461, and we can do what you can do is make a directory L16 theory compare. Let's just do a make directory L16. Okay, and then cd into L16. All right, so now note that over on the Canvas site, there's a couple of things. Of course, you have the PDFs I make, which, by the way, has information in it that we're going to eventually plot. So, if you go through that, you'll see that, let me open this up. We have plots that we're going to actually compare. We're going to look at MATLAB, and we're going to look at Abacus here. Note that these things are really important. So what I find is that when you go through this process, you're basically we're going to prove that Abacus gives us the result that we expect, because we derived it by hand. We're basically going to make it automated algorithm in MATLAB, which will give, basically, I call that kind of like the hand results. Basically, it's using a calculator, the MATLAB, to calculate our hand results. Okay, so a couple of things before we get started. If you go over to the notes, all right, there's a couple of things. First is obviously the PDFs that are up there. And if you look in there, you notice that I've got results in the back end of that presentation. So let me go over to the slides. So we actually are going to go through some MATLAB code. This MATLAB code is not the affine element. Well, it's got components of the affine element method in there, but it's not a affine element program. All I'm using it as basically, as you can see, I'm using it for matrix math, and I've transferred my hand calculations into this MATLAB code. I'll take you through that. So the purpose is just so I can put different values in and compute the results really quickly. It's more like a calculator than it is like an implementation of the affine element program. And then the second piece of that is Abacus. We're going to compare Abacus to basically our hand calculations that we do in MATLAB, if that makes sense. The purpose here is that we're going to prove, if you use Abacus, what's the problem with it? The problem is that we don't know what's inside of it. We don't have the source code. We don't know really how it's computing things. And so this effort is to basically prove that we understand what's going on in Abacus, because we get the same result as deriving it by hand. That's the sort of the purpose, is to prove it to ourselves. And I actually do this a couple times, where this is what we're laying here is the foundation of what actually will become one of the exams. And the exams, you sort of have to go through this similar process. And again, the purpose here is to prove that we know what's going on internally to this black box, this Abacus program that we use. So with that, let's sort of get started here. The other thing over on, you have a couple of options. You have a MATLAB code, .m file, and you have a guide to creating the check that we're going to do. So you have some resources there, and also we walk through creating the Abacus file, but you also have a CAE provided there as well that you can just open up. So what we can do is download these items and maybe bring them over to ACI. This one we won't download, so then I need to go over to my files and my home directory, go into work, classes, go into that L16 directory we made, and we're going to upload those two files we just created. Downloads, this one, and then we will also do this one. Okay, so we got those files there. Let's go back now to check the, yep, they're there. So now we can load up MATLAB, module load MATLAB. MATLAB, you can just use the ampersand so I can run it in the background. Load that up. Okay, so I have some old stuff here. So we can open up this check all with 1. All right, so we're going to go through this later on too, so I don't want to spend too much time on it, but basically what we're doing is we're giving variables. Okay, so we have 2 elements, right? So we have cross-sectional areas, some variables up front we define. Young's modulus, we said that's going to be equal to 1. In our last video, we said to simplify it, let's just assume all this stuff is equal to 1. And again, we're in kilogram meter second. And then our force at P2 and P3. We calculate those constants here, and we put those into our global matrix. You see it's like pretty manual. There's no like algorithm I use to create this global stiffness matrix. In our real finite element code, you would have an algorithm that would actually iterate through elements and use the connectivity to put those in the right things. Here I'm just typing it out. We'll actually get to that later on. Global force vector, you see I specify those. I then use the elimination approach to create a reduced global stiffness matrix, and I just select which rows and columns I want to save. Same thing with force. I then solve for the global displacements using the inverse of that reduced matrix that MATLAB computes very easily for me. And then, so that's the Q. I then compute the B matrices for each of the elements, and then I create a global matrix, Q global, which has my boundary condition in it, as well as my reduced values that I just solved for. And so that allows me to create a Q element 1. I mean, I don't necessarily have to do this, I guess. I'm just making the local displacements for element 1 here and element 2 using the displacements that were obtained through the solution procedure. I define the strain, so it's B times Q, and then stress, E times strain. And then, so that's pretty straightforward. I do that for the second element. And then finally, I compute the reaction force by using the values associated with that first node where our displacement boundary condition was applied, along with the equation that we presented before. Okay, so we run this. We say run. We get all these values, and then the question is, and some of these are the values that I plotted in the PowerPoint, so I actually do screenshots and put them there just so we can compare later on, but this is how I obtain those. All right, so our next step is we want to actually create a abacus file of the similar problem. So let's go ahead and do that. We can minimize MATLAB here. So in the abacus, you think about how you could do this. You should be able to walk through this in your mind mentally, I think, a little bit, like how you go ahead and create this problem. We've got enough experience. You should start to be pushing, your confidence level with abacus up a little bit more. So module load abacus BGL run abacus CAE. So here we are. Now I'm going to set my background like I like to do, although you should be able to create this pretty quickly. I'm not going to spend a lot of time on it. I'm going to show you, how quick it can be to actually create this problem, I guess. So my speed will be a little increased, but you can pause it, I guess. Okay, the first thing we can do is create a part, and we'll do a 2D planar with a wire. Continue. We'll go ahead and put our coordinates in. So we'll have a 0, 0. Our next one's going to be 1, 1, 0. And our next one's going to be 2, 0. Okay, because everything has a length of 1, right? So there's our geometry. Go into property, define a elastic property. We're going to use static problems. We don't need density. Young's modulus is say 1, and Poisson's ratio doesn't matter here because we're going to be in a truss element, but we can just put 0.25 so it doesn't complain. Okay, we're going to create a section, which is going to be a beam and a truss. So we say okay, and it automatically picks up that material with the correct cross-section area. It assumes of 1. We say okay to that. We then assign these parts to a section, this part I should say, to a section, and it's automatically picks it up. Say done, it turns green. We then can go on to the assembly. All we need to do is have that selected and say okay, and we then go create a step. We'll create a static general step, and time period 1, we can leave all of this, take the defaults. We don't have any interactions. We do have a load. We can do a boundary condition, displacement, rotation. We're going to select this node here, say done, and that's going to be equal to 0 and 1. Now because we're 2D here, we need to specify these other things as 0 as well. In our analytic solution, we didn't have that. Okay, so the next thing we want to do is apply the point forces. So concentrated force, we have one here, and we can actually, because they're equal, we can apply them together. So we have 2 nodes, and they're actually applied in the same direction too. So that's going to be equal to 1 here. Say okay, and there's our point loads. Now the next thing we can do is move on to the mesh, and here where we seed the part, got to go part. When we seed this thing, it tries to give us a global seeds of 0.1. So if we were to accept that, we'd have lots of these little elements, right? We don't want that. In this case, we want to try to mimic what we had in the hand calculation. So we want to force the element size to be 1 in length. Okay, so we just want 1 element. So we say apply, and there that seed would give us that value. Say okay. We then can mesh. Say okay. And then what we need to do is make sure that this is really a truss element. So if you go down here to assign element type, select this, say done, and you notice that it comes up as a beam. So we actually want to change that down. See, it's a 2D by linear beam in a plane. We actually want to change that to a truss, 2D linear 2D truss. And that's kind of, we haven't been doing 2D, but it's very similar to what we're doing. So we say okay there to the truss, and we then have our mesh problem defined. One thing you got to check is, or one thing to note, actually, if you go into View Part Display Options, okay, you have a tab there for mesh. So let's do Show Node Labels, Show Element Labels, Apply. All right, so what's interesting here, this is node element 1 and element 2. So that works, that matches what we had. But what you notice is that Abacus is smart, and it assigned 1, 2, and 3. These node values do not correspond to us. So basically 1 matches, but Abacus's node 2 is our node 3, right? Because I switched it up to make it a little more complex. So their node 3 is our node 2. So we have to keep that in mind when we run this result and compare to our hand calculations. We have to swap those. All right, so okay. And now we can create a job and submit that job. All right, that job completed successfully, so then we can go into the results. And we can look at the deformed configuration here. So there's a couple ways to extract results out of Abacus. If you go into the PowerPoint here, you see that, let's focus here on this first plot that I create. So we're looking at the displacement at these different nodes. So I want to actually show these node numbers again. There I have the note that this is node 3 in MATLAB, this is node 2 in MATLAB. So what we calculated was here, if you remember, was 0, 3, and 2. And so we want to look at that displacement value might be the first thing to do before moving on to stress and strain. Right? Abacus gives us stress right away, then maybe that doesn't make sense. So let's go into the displacement, and we're going to actually, here you have to specify which direction, because in our case we might have a little bit of U2 because we're 2D and the node can move in 2. So in reality we probably should have constrained nodes, all the nodes, in the Y direction so they could only move in the X. Because we're applying the force in that direction, it probably doesn't matter, but to be, you know, absolutely sure, we should have done that. But we can look at U1 here, and there, let's go ahead and turn on the node numbers. For that, we go into this one here. So we go into common options, this button here, show element labels, show face labels, or no, not face, show node numbers, show node symbols, say apply, and there we can see that, you know, the red is 3, and so that displacement looks good. So that's our node 2. So if you go back, our node 2 has a 3. So those are looking good there. And go back to node 2 here. It's kind of like in the 2 color, which corresponds to our node 3, which is 2. So these results are looking really good. You can do a quantitative, more of a quantitative plot for this if you go into the field options. So go into ODB field output, say continue. You can look at the, say, unique nodal values. You can look at this, the plot of U1 here, and then you have to select which node. So you could do edit selection and select this node 3 here and say plot, and there you can see the displacement of 3. And again, it doesn't matter the time. You basically want to look at the very last, whatever time you used. I mean, I assume you used 1, but you want to look at that very last position, and that's 3. To get even more of a quantitative look at that, what you can use something called report options. So if you go to XY data on report, and we don't have any XY data here, so we actually need to go to plots. Let me move this a little bit. Okay, and so we want to save that data. So that goes into the saved category. So now if we go to report, go to XY data, we have some data here that we can look at. So here we just say apply, and again, you have to look at what this is. This is the displacement in the one direction, the X direction, for node 3. So we say apply. So, okay, now what happened was, if you look down here in the information panel, it says a report was appended to this file, abacus.rpt. So if we go back to our directory here, and we see, go ls-ltr, we see that there's a rpt file here. So you can open that with a command called gedit, and then abacus.rpt, and maybe the ampersand there. So this is what that data looks like. Looks like I wrote it twice, but it gives you at the different times, this is X is time, it gives you the value of the displacement. Note that at the final version, that's what we care about right here, it's exactly 3. So there's no like, you know, round off error. It just, you know, it will give you, if it's off a little bit, it will give you like exponential values, but this was exactly 3. So that result is a really good one. It compares exactly to what we computed in the hand calculation. Okay, now you can do that whole process again. You can do it for, say, if you wanted to change that to, we actually have to go back to the deform configuration. If we want to select a node, we can change that to node 2. Here, say plot and dismiss, and you can see that this one is equal to 2. We can save that, and then you go to report, you can write that one out. So if you want to select this one, you say apply, and it says the file was appended. So if we go back now to our gedit report, you see you get this comment that says it was changed. Do you want to reload it? Yeah, let's reload it. So then we have data 2, and this corresponds to that value we just wrote. And there you see our final value is 2, as we expected from our hand calculations. The same way is possible with stress. And then maybe actually the next thing you probably go to is, say, strain. Okay, and here you want to do the 1-1 calculation, and notice that the strain is constant in the elements. Okay, so it's all 1 or it's all 2. Okay, we can plot that value and go to field output. But first, by the way, the strain is 2 in 1 and it looks like 1 in 2. So let's go back and see how we compare. All right, so here from the MATLAB, this is a screenshot of the results. In element 1, it was 2. Did I skip one? Element 1, it's 2. Element 1 is 2. Okay, so element 1 is 2. So we are actually computing the same result there. We can plot it like I showed you, and we can save that in the same way, appending the RPT file if we like. So it's pretty standard. What you find is that we go on now to the strain here. What are we looking at? We're doing in element 2, we also get the same result, 1, and you can see here the plot, strain versus time. At the last value, it's equal to 1. So we're getting really good results here. Exactly, they match exactly. And then we go on to stress. It's the same story. We match very well, and the reaction force is the same way. To do the reaction force, there we got a -2. So if we go back to reaction force in the one direction, you can see that at the blue it's -2, which is at node 1. Okay, and that node matches our node, so it matches exactly. All right, so that concludes this lecture. We've now gone through by hand calculations. We put the hand calculations in MATLAB basically for a calculator, and then we ran Abacus of the same problem. We saw that gave exactly the same result. So this should instill some confidence in you. This should excite you that you understand what this black box is giving you. It's not so much a black box anymore. We're starting to break those barriers down. So we have a really exciting application coming up next, and then we're going to move this theory on from using linear shape functions onto now more complex quadratic shape functions for the truss. So I'll see you next time.